Hey Candy, let me ask you something. As you can see, the athletes are cycling on the oval track. Is there a way for them to ride under the track?
What? Cycling under the track? Like upside down? But you need to define gravity first.
Taking gravity out of the equation, how can you ride on both the top and bottom of the track? Here's a model train track. It has a surface and a subsurface. In normal situations, the train can only go round and round on the surface of the track. Now Candy, can you find a way for the train to travel on both the surface and subsurface without leaving the track?
It's impossible.
Don't restrict your thinking to accomplish facts. Try to change something and check whether it works. For example, the train or the track. Here is a strip. Think of it as the track. Make changes to it and try out some simulations. Then check the results in a real situation. Remember, most problems are solved by trial and error.
The train cannot leave the track. So it seems that the train could not be changed. Let's try and change the track. Both ends of the strip are glued. Assuming the strip is the track, the train must run on the surface and subsurface without leaving it. If both ends of the strip are glued after it was twisted through 180 degrees, supposing this pen is the train, when I draw a line from here, it goes back to the origin after one round. A line has been drawn on both the surface and the subsurface of the strip, but the pen hasn't left the strip. Yes, I did it!
Candy, you've just made a Mobius strip. This is a single continuous curved surface. Let's twist a rectangular strip through 180 degrees and then glue the two ends together. See? A Mobius strip is made. You've already made a Mobius strip. By observation, can you tell me the properties of a Mobius strip?
A common strip has two faces, that is, the surface and the subsurface. The Mobius strip only has one face. There is no internal or external surface. The special property of this single continuous curved surface is that it has only one face.
The geometry we learned in secondary school is Euclidean geometry. However, the Mobius strip is a topic in topology.
What is topology?
Topology seems to be quite a strange area of study, but many examples in our daily lives have something to do with it. This is one such example. There are 4 points here. Can you connect them with lines so that each point is linked to the other 3, but without having 2 lines intersecting?
How would you connect the points?
Let me show you. Topology can be applied in many aspects, such as games, computing, engineering, and logistics. But the areas in which topological concepts are most commonly applied are games and magic tricks! Ta-da! Topology is a branch of modern mathematics, the content of which is special and abstract. The properties of relationships between figures and the relationship between figures and their spaces are some topics covered in topology. Recently, some topologists studied the results and statuses of objects after they've been bent, twisted, pressed, or extended without being broken.
To study the results or statuses of these objects after being twisted or pressed, these objects must be very flexible, mustn't they?
Yes, they must, but our thinking must be flexible first. In Euclidean geometry, the cube, rectangular block, and sphere are three different kinds of 3D objects. However, in topology, these three objects are topologically equivalent. Simply put, in a topologist's eyes, the shape or appearance of these three objects are the same. They are all closed 3D objects. By the nature of topological equivalence, a closed 3D object can be a sphere, cube, cylinder, or cone.
It's because these objects have been compressed, twisted, or pulled apart without being broken. After transformation, the appearance of an object changes to that of another object.
Correct. These transformations are similar to how we keep changing the shapes of modeling clay, but the properties of the object itself do not change. Here's another example of topological equivalence. The gloves for our left and right hand are quite similar, but they're not the same in nature. They're unique. It's uncomfortable to wear a left-hand glove on our right hand, and vice versa. No matter how the glove is twisted, a left-hand glove will always be a left-hand glove, and a right one will always be a right-hand glove. When the concept of topological equivalence is applied to these gloves, there is no left-hand glove or right-hand glove. There is only a glove with a shape of 5 fingers for both hands. Comfort and fit are a matter of personal perception. We've already discussed some topics covered in topology, such as the Mobius strip. Let's explore the properties of the Mobius strip further. We can't explore the properties of a Mobius strip just by discussion. The rule of thumb is to learn by doing. We should explore the properties by tampering with the object.
But the strip is not modeling clay. How can you compress or extend it?
Try cutting it.
You just said the objects cannot be broken, didn't you?
I didn't ask you to break the Mobius strip. Try cutting the Mobius strip along its central line with a pair of scissors without leaving the strip, and see what you get.
A large Mobius strip.
Is it really a Mobius strip?
I'll draw a line along the strip and check whether it can go through both sides. The line can't go through both sides of the strip without lifting the pen. A line can only be drawn on one face of the strip. I'll correct my conclusion. The large strip is not a Mobius strip.
If a Mobius strip is cut along its central line, the strip turns by 360 degrees. It is no longer a Mobius strip. The length of the new strip is doubled, and the width is 1/2 of the original strip. Candy, please divide the Mobius strip into 3 equal parts and 4 equal parts by cutting it 1/3 and 1/4 along its width respectively. See what the results are after cutting.
Okay, let me divide the Mobius strip into 3 equal parts first. I'll cut the Mobius strip 1/3 along its width. I get 1 large and 1 small twisted strip. The large strip is not a Mobius strip. It turns by 360 degrees. Its length is doubled, and its width is 1/3 of the original strip. The small strip is a Mobius strip. Its length is same as the original strip, but the width is 1/3 of the original one. Now I'll cut 1/4 along its width. Just as before, one large and one small twisted strip are formed. The large strip is not a Mobius strip. It turns by 360 degrees. Its length is doubled, and its width is 1/4 of the original strip. The small strip is a Mobius strip. Its length is same as the original strip, but the width is 1/2 of the original one. From our observation, there is a line of equal segment left on the Mobius strip. If it is cut along this line, a strip which turns by 360 degrees is produced. This new strip is not a Mobius strip. Its length is doubled, and its width is 1/4 of the original one. That's so amazing!
If we cut the strip 1/5 along its width, the result is similar to the previous cases. Candy, you can try and keep cutting. We've already discussed the properties of the Mobius strip and explored its formation. Now let's think about how the Mobius strip can be applied in our daily lives.
Since the basic property of the Mobius strip is having only one face, let's attach the Mobius strip onto two wheels and create a conveyor belt.
How did you come up with such an idea?
Wear and tear only occurs on one face of the traditional conveyor belt. If a Mobius strip is used, then both faces of the belt will be exposed to an equal amount of vibration. I believe the life cycle of this belt would be longer than a normal one.
This conveyor belt design utilizing the Mobius strip is very practical and creative. However, the belt is turned 180 degrees and there's a knot at the pivot point. Feasibility and performance needs to be further evaluated by professionals.
Can this property of the Mobius strip be applied to the design and production of tapes or ribbons for tape players, printers, correction tapes?
That also needs to be evaluated by professionals. Previously, we discussed how the Mobius strip can be applied in our daily lives. Because of its uniqueness, some entrepreneurs or designers have used it as an element in company logos or product designs.
Here is a value-added card. Adults, children, and elderly might have at least one. Have you ever noticed the logo on this card?
Maybe you can see the number 8 by turning it through 90 degrees.
The logo on this value-added card is a Mobius strip. It seems like a number 8 or the infinity symbol at a glance. If it's a number 8, it echoes the brand name. If it's the infinity symbol, it implies the infinite functions of the card. You can use it for traveling, payment, shopping, or even recording attendance.
Let's take a look at the logo for the Hong Kong Sustainable Development Research Institute as shown on its webpage.
The logo design is inspired by the idea of Mobius strip. Because of the strip's special structure, if you imagine a person working his or her way through a giant Mobius strip, he or she will never stop. This alludes the idea of continuity and the perpetual nature of sustainability. Johnny, today we have focused our discussion on the Mobius strip. I think I need some time to digest.
We can also think about the particular properties of the Mobius strip as well as its applications.
All in all, our thinking must be flexible, just like the elasticity of the topological objects.